Shouldn't I worry myself with what the graph
When
is?
we're checking the diagnostics for regression, and this could be simple linear regression or multiple linear regression, one of the conditions is linearity, right? And what we mean by this is that if you have a simple linear regression where you have just a y and an x, right? You want to make sure that the relationship between them is linear, that it would be wise to fit a line like this than, say, a curve like this, okay? You can check this by using a scatter plot of y versus x, or even better, you can check this using the residuals plot. And that residuals plot is usually your residuals, so versus your predicted values, y hat. That's the residuals plot that R will spit out for you. The reason why you might want to take a look at the residuals plot as opposed to the scatter plot of the actual data is because if there is a minor deviation from linearity, that might be hidden in the scatter plot. It might not be that easy to see. However, a residuals plot will exaggerate that. Okay, so something, for example, in your y versus x, let's say that you have data that look just a little bit like this, okay? That's not a line, but the curvature is so little that you might miss it. But probably in your residuals plot, that's going to look like this, okay? It's going to be a lot more exaggerated, and it's not going to look like a random scatter around 0. When we're dealing with, so this was for the simple linear regression case, where you have only one explanatory variable. When we have multiple linear regression, we again want linearity between your response variable and your explanatory variables, but this time you have many explanatory variables. So then really what we're looking for is a linear relationship between y versus the numerical x's, okay? Because you can't really have a linear relationship between, let's say, exam score and major. Like, that's a categorical variable, the major. You won't be able to see a linear relationship. But between exam score and number of hours studied, like, there might be. If there was going to be a linear relationship, it would happen with the numerical explanatory variable, not the categorical. Again here, the way we check this is looking at the residuals plot, okay? So we definitely don't want to be looking, there can't be a scatter plot that visualizes your entire model if you have multiple explanatory variables, because that's not going to be two-dimensional anymore, right? What you're fitting really in a multiple linear regression, you're fitting a plane really, you're not fitting a line anymore because it's not a scatter plot with 2 dimensions. So we can't really visualize that, but we can synthesize all that information down to 2 dimensions with a residuals plot of y hat versus the residuals. So this y hat is the predicted value of your response variable based on that model. So it incorporates all of the explanatory variables into it, if you think about it, because how do we calculate y hat? That's your beta 0 plus beta 1 times x, b0 plus b1 times x1, b2 times x2, b3 times x3, so on and so forth, right? So you would have gotten information from each one of your explanatory variables, multiplied them with the slope coefficients from the model, added the intercept to get to this predicted value anyway, okay? So that's on your y hat. Now, if this plot looks good, then you're good. Linearity condition is satisfied. But what if this plot looks bad? What if this plot looks something like this? Okay? Now what we decide is linearity condition is not satisfied. The next question might be, can I figure out which one of my explanatory variables might be causing this? Because if I can figure that out, maybe I decide, maybe I won't have that explanatory variable in my model, or maybe I'll apply some transformation to that explanatory variable to make things look a little more linear. And we'll talk about transformations a little bit at the end of the class. You can do things like taking the log or something like that and see if that makes life better. Now, in order for that investigation, though, overall, in this red, line, we're seeing something is wrong with the model. But that doesn't tell me if which explanatory variable might be behind this. So in that case, you might then want to look at individual plots of, let's say, your y versus, your response variable versus your x1, or your residuals versus your x1, and similarly your response variable versus your x2, or your residuals versus your x2. Like, take a look at these and see which one of these is the one where we have a nonlinear relationship that might actually be driving this. So you would only do this investigation of going through each one of your explanatory variables if you saw something like this where something was wrong. If you decided, no, my linearity diagnostics check, my residuals plot of predicted values versus the residuals look like a completely random scatter, you're not going to go investigating further. Okay? So what you'll see in the book questions is sometimes you'll be provided all of these plots, but you might end up not using them. Because in the book question, where you're not the person making the plots one by one, we give you all of the plots, and you might decide to use them because you had an issue like this, or you might decide to not use them because the first plot looked fine anyway. Okay?
And, okay, I guess that's sort of, so my second question had to do with like the same plot. And so basically the residual, and well, both of them, I guess, are taking into account the entire, like you're using the entire equation.
Yes, both the residuals and your y-hats take into account data from all of your explanatory variables as well as your parameter estimates.
Okay, so like for the x-axis, it's like put in x equals 2 for every single one numerical variable, and then you get a predicted y-hat.
So what you do is, the way you calculate the y-hats is this. So for example, let's say you have a data set, okay, where each observation is let's say each observation is a state, okay? So you have a data set of 50 observations, okay? And for each one of my states, I know things like unemployment rate, or let's say I'm trying to figure out what unemployment rate is, okay? And let's say that I know things like median income and the region where the state is in, so some categorical variable, okay? So for example, in the first state, let's say my unemployment rate was 8%, median income was, $40,000, and the region it's in is in the Southwest. For my second state, let's say unemployment rate was 7%, median income was $42,000, and this is in the Northeast. So I have data like this, okay? I fit a model where I try to figure out what's unemployment rate, predicted unemployment rate, based on, I will calculate an intercept. So first slope times the median income plus the second slope times region, right? My model will look something like this. Obviously, there's actually going to be many other slopes estimated because region is a categorical variable, right? So then once I calculate these, so let's say region has 3, how many levels would it have? Southwest, Northeast, West, south. Let's say it has 4 levels, okay? So this would look something like this, right? Because 4 levels of region, I would calculate 3 slopes for it. So what my model output will give me is these numbers, right? All of my slopes and my intercept, that's going to come out in the regression output. Now what I do to calculate my y-hat is I actually go back to this data, right? And then I actually calculate my y-hat for each one of my observations. So I go to state number 1 and I plug in 40,000 for its income, and I plug in, if Southwest is the first region, for example, maybe I only plug in this and give zeros for the other regions, and that will spit out a calculated unemployment rate for me. So that's going to be my y-hat, right, my unemployment hat, so I can calculate that. And similarly, I go in and calculate this on predicted unemployment rate for each one of my states. Now, actually, when I say I go in and calculate it, when you're doing this in R actually does this automatically for you. It's what R calls the fitted values. These are the fitted values that you can get from your model. So that's on your residuals plot. That's what goes in your y-axis. Now, what we said is that we also have the residuals, right? And how do the residuals get calculated? What's the definition of a residual? It's the difference between the observed and the expected. So basically, if you have the true unemployment rates for each of your states, and you have the predicted unemployment rates for each of your states, your residual should be?
0.
Why would it be 0?
Wait, did you say that? Oh, you said if the...
Let's say, for example, that for my first state, I had calculated unemployment rate to be 8.5%. What would the residual for that state be?
0.5.
It would be negative 0.5, right? Let's say for the second state, I had calculated my predicted unemployment rate to be 6%. What would the residual for that state be? Positive 1. So I can calculate all of those as well, right? And then what ends up going in my scatter plot is those combination of data. So 8.5% and negative 0.5%. So maybe that first point is somewhere over here, okay? If this is the 0 residual. Am I doing this right? No, I did not. Sorry, I have the axes swapped. That's why I am. It's residuals versus your predicted values. Okay? So yes, the first one would have a negative residual and a positive predicted. And then the second one would have a positive residual. We said a positive 1, but a 6%. So maybe it would be over here. So that's how I would fill up my residuals versus y-hat plot.
So the order of filling up the graph doesn't really matter.
No, the order in which you fill it up doesn't really matter. All we need is the predicted values that you can calculate once you have your parameter estimates. And similarly, imagine adding a new column here of your residuals, right? Which is the differences that we calculated. So for each observation in your data set, it is possible to calculate your y-hat, and it is possible to calculate your residual. Okay?
And so that's my last question had to do with like the order of data collection, so independent residuals. I guess it sort of has to do with the same thing. So it's like you check using the residuals versus further data collection. And so part of data collection, do you mean just like how we have like the 1 through 50, which is like x, or like whatever the x variable 1 is like number 1 observation?
Yes. So exactly. So the order of data collection. So when does that come into play? Another one of our conditions is independence of observations, right? Or you can think about it as independence of residuals. Now, one way of thinking about are my observations independent is based on the sampling method. Like if you know that you had a simple random sample that you collected data from, then you know that you actually have independent data, right? Now, another thing is we can take a look at order of data collection. And this is something that becomes relevant when we have time series type data. What we mean by time series data is data collected over time. Now, that doesn't mean somebody was like sitting there with a clipboard collecting the data over time. It can. It doesn't have to mean that. It could mean something like you collect data, let's say you look at unemployment rate over time. So your X is the year, and your Y is unemployment rate, for example. Okay? So in 1990, unemployment rate was blah. In 1991, it was blah, so on and so forth, all the way to 2016, unemployment rate was blah. Okay? If unemployment rate in 1 year is dependent on the previous year, then you don't have independent data anymore. So then this condition is violated. How might you check this? The way we check this is we plot our residuals versus the order of data collection. And in that case, what we're saying is this was the first point that was collected, this was the second point that was collected, so on and so forth. And so those make your ticks on your x-axis here. And whatever the residuals are, just like we showed earlier in the other example, we can calculate residuals. We can still calculate the residuals for each one of these data points and plot them over here. If you see a trend that's like as the order increases, your residuals increase, or as the order increases, your residuals decrease, or so on and so forth, then you know that there is a problem, right? If you see instead that as the order increases, the best fit line for your residuals would look something like this, around 0, then you know that there is no trend. Then we can talk about independence of your residuals. This only becomes really relevant if you have time series type data. If you don't, then it may not be worthwhile to check in the first place.
Thank you.
You're welcome. So I think that in one of the first slides that we were writing up, we made a mistake. I made a mistake in terms of talking about the plot. So when we talk about the residuals plot, it's your residuals on the y-axis and your predicted values on the x-axis. Okay, I think I switched them in the first plot when I was drawing them. Okay? And because it's your residuals, this is usually what it looks like, because if that's the 0 residual, you would expect some of your residuals to be above 0 and some of them to be below 0, because that means that in your actual scatter plot, you had maybe data like this where some of the data were above the line and some of them were below the line, resulting in some positive and some negative residuals. When might you always have negative residuals? If you put your line like this. But obviously nobody would fit that red line if your data was these black dots, right? That's ridiculous. Or this is also ridiculous where all your residuals are positive. So when you have a cloud of points, what we do is we actually, our best fit line goes through the center of them in some way such that you have some positive and some negative residuals, which means on your residuals plot, some of the points are above the 0 line and some of them are below it. Okay? Any other questions? Let's take a look at the book to see. Maybe we can do one question together and then Okay, so how about we do question... I actually like question 8.6, but I think that's in your homework anyway. Let's do question 8.6 anyway. Really, I'm interested in question 8.6b because that's kind of getting at what we were talking about, okay? So we have this timber yield that's approximately equal to the volume of a tree. However, that's very difficult to measure without first cutting the tree down. So what we do is we collect data on things that are going to be easier to measure, like the height of a tree and the diameter of a tree. And based on this, we can fit a model to figure out, based on trees that were cut, where we actually had their volumes as well, we can actually figure out a model for estimating the timber yield or the volume. And then for a new tree where we don't have the volume information, we can use its height and diameter to make a prediction for it, right? So what we're seeing here is that the predicted volume of a tree is the intercept, negative 57.99, plus the slope of the first variable, height, plus the slope of the second variable, diameter. Okay? So in 8.6b, we are told that one tree in this sample is 79 feet tall and has a diameter of 11.3 inches and is 24.2 cubic feet in volume. Determine if the model overestimates or underestimates the volume of this tree, and by how much. So how would I go about solving this problem? So this is a tree in my sample, so I know everything about it. I know its height and diameter, and I also know its volume. And what I want to figure out is if the model overestimates or underestimates it.
So you would use your equation, and then you would plug in everything except for the volume.
Exactly. We would use this equation and plug in everything except for the volume, right? Because what we are trying to figure out is what is the predicted volume of this tree. So I would plug in its height, which is 0.34, and I would plug in its, whoops, sorry, that's not true. That's the slope. Its height is 79 feet, and its diameter of 11.3 inches. And I would, based on this, figure out what is its predicted volume. So that's just a simple calculation question. So that's negative 57.99 plus 0.34 times 79 plus 4.71 times 11.3. So the predicted volume of this tree is 29.023. Okay? Sorry, 29.093. Determine if the model overestimates or underestimates the volume and by how much. So this is the predicted volume. And the real volume of the tree is 24.2. So does my model overestimate or underestimate? Under, right? So my model underestimates. And by how much? So that's going to be my residual, right? So I can calculate my residual as the observed volume minus the predicted volume. So that's 24.2 minus 22.093. So that's 2.107. Okay? Now, obviously, it doesn't matter in which order you subtract them. If you're just trying to say, oh, it's off by 2.1 or something like that, but I purposefully left them in this order because the definition of a residual is always observed minus predicted. So what we can see is that if the observed value is above the predicted value, you have a positive residual. So that's in your scatter plot, that looks something like this. This is your predicted, right, on the line. And your observed for this particular tree must be somewhere up here. It's above the its predicted value. Okay? So we can see that for any observation in our sample, we can calculate the predicted value and we can calculate the residual. And that's what R does every time you run that LM command for all of your observations. If you had to do each of these by hand, that's going to take some time, but R does it just like in a split second for all of the observations in your data and actually stores these numbers for all of the observations in your data so that when you want to make plots, you can just say, hey, you had already calculated and stored this. I'm going to grab that now and put it on my plot. Okay? Any other questions? No? Okay. All right.